Hey guys, was gonna record today's Daily Code Forces video, but Code Forces has been down for like the past, I want to say 2-3 hours, and I'm not sure if it's coming back up anytime soon, or at least before 12 o'clock, so I still wanted to output a video for y'all, so I guess, kinda sucks, because I was gonna continue the streak, but this might just cut the streak off again. And I guess I could have done Code Forces earlier in the day, but I had homework to do. Like I was doing homework right before this. Um, and before that I have school, stuff like that. So yeah, this just really fucking sucks. But I still wanted to get a video out for y'all, and I still want to like practice, like do my practice today, right? So we'll turn today into day 8 of the CSES problem set, and we'll just keep working along on that. Um, totally fine. The CSES problem set do like feel harder, or at least the introductory questions have felt more ad hoc than the Code Forces problems that I've been working on. So it's not a bad trade-off. I hate to break the streak again. Um, it feels terrible, but there's not much we can do about it if the site is down, right? So yeah, let's just get right into it. Solve some problems. Tower of Hanoi. So this was the game where like it's the stacking game, and you want to move like all the discs from stack 1 to stack at the end in this same order, right? Left, middle, right, in round discs. Initially, the left stack has all the discs, and okay, the goal is to move all the discs to the right stack using the middle stack. On each move, you can move the uppermost disc. My bad. Um, you're not allowed to place a larger disc on a smaller disc. Minimize the moves. So this is basically just Tower of Hanoi. So we basically have 30 sticks. Let's use what's provided for us. Spread them out a little bit. 3 sticks, and then we have these discs. And how many do we get? I assume in, right? Number of discs. So let's just do 3. For this example. And what we want to do is we want to end up with the same at the end, and we can only use the middle to move things around. So let's see if we can find a pattern in this, at least with 3 base. So first we would have to move this to either this one or this one, right? It doesn't really matter in this case. Then we move this to the other one, and we move this back. And then we move the long one, move the small one off, and stack it. Okay, so that's pretty simple with 3, but how does it work with 4? Again, the first move doesn't really matter, right? Second move is just the next empty. We move the second onto the first, and then this one, and then we move the top one onto empty. So now what do we do? We move this here, no, other way around. We move this here, this here, this here, this here, and then here, here, here. I even doing this optimally? Let's start from start. Let's start from 3 again, and like actually look at how a solve looks. So 3, 2, step 1. Next step is okay, like this. And it's like this, 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 this. So this takes 1 move, 2 move, 3 move, 4 move, 5 move, 6 moves, 7 moves. Wait, 3 moves? What are we outputting? Our only input is n equals input, but first print k, the minimum number of moves. After that, print the k lines that describe the moves. You move a disk from stack A to stack B. Huh? A and B. Oh, so you move a disk from stack 1 to stack 2. I get it. So 3 moves. From stack 1 to stack 2. Well, our input's 2 in this case. So 2 disks. Stack 1, stack 2, stack this 1 to 3, and then 2 to 3. And then next one is 7. I don't know why I made these disks so big, they take up so much space. The next one is 7 moves. 1 move, 2 move, 3 move, 4 move, 5 move, 6 move, 7 moves. It goes 2, 7, and then 1, 2, 3, 4, 5, 6, 7. Okay, but this could totally be like here, right? So my stack order is kind of off. Instead, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 2, 7, 15. So is this a recursion problem? Like, do we always start from the same moves? So in the case of 2, we did 1, 2, 3. In the case of 3, we did 1, 2, wait, 1, huh? 1, 2, 3, 4, 5, 6, 7. Wait, so what was our starting move? It was 1. It was in the second place. We skipped 2, but in 2 we skip 1. In 4 we skip 4 we skip 1. So skip 1, we skip 2, we skip 1. Gosh, this is hard. See, I never really considered Tower of Hanoi like past like case 3 before. Like, when I thought of this game, like what is the optimal way to Tower of Hanoi? There's 3 stacks in discs. Move all the discs. Well, we basically have 3 queues, right? Or no, not queues. They're stacks because we can only take from the top. So our first step is to always move the base to the last. We want to move the largest. So step like rule 1, always move largest to right. That's our first step, but that means we need at least two to find the largest, because if we do this largest between 1, then you'll have the itty bitty one. So, like this. If we consider what largest to right most, we do this. And then this one goes here. And 3. So that's no good. So we consider okay, so we can order the stacks. Like we can give a priority to the stack. Like as in closer to this way equals better, and then higher up is better as well, or something like that. So and then we look at the two best at all time. The two best movable at all time, right? I think that is going somewhere. Let's check, because I think this works for 2, where the two best movable are this one and this one. Or no, this one's not movable. The two best that okay. Instead of calling it two best movable, it's the best movable and the best largest to the right. And the best unmovable. Okay, I need to simulate this again. So we're looking at these two. The one under is obviously bigger. So we want maximize. And then in the case of 3, one under it is bigger. So we maximize. Hmm. Bang. 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 Now in this scenario, bang. 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 Okay, so low key, after you get the biggest to this side, it becomes a recursive problem of the previous problem, because we are treating this is n2, right? So it's literally largest to right plus dp n minus 1. And we just construct like dp equals n. Right, now base case is n equals 2. The base case is n equals 1. 1 is 1, 1, 3. So n equals 2 would be, get to the left first. So 1, 2, and then plus 1, but it's 2, 3. Is it always 2, 3? If we look at 4, one, 2, 3. Oh, looky, this is recursive too, no? When we're building this stack. Or is it? Okay, this is 7 moves. Here. And then this is recursion. So we basically have to do recursion. Like, this is just a recursion problem. The hard part is it flips around a lot. So how we actually save the data is kind of difficult. Mm. Can we brute force this? No, brute force would be way too hard, because then you have to determine, like, well, is it too hard? It's like just determining the position of where you move the first one is not obvious to me. Because what if with 5? What if we have 5? We got it over there. It took 20 strokes. Hmm. This is 3, not 2. I don't think that changes much, but that was throwing me off. It was 1, 2, 3. N equals 1, N equals 2, N equals 3, N equals 4. Well, at the end, we just have something like, I have a moves array, and then print len moves for move in moves, print star move. This is what our output looks like. Now, how do we do this? Mm. Mm. So, I want to see if this is a case where so you have 3. Okay. We have 4. Okay, so we always want to build the previous problem in the center, right? Is that the case for 5 as well? Where do we go?
Okay, so before moving the last one, we build the previous problem in the center. Okay, what does that mean? In the simplest case, we're working with n equals 1. What do we do? We would straight up just move it to the end. In the next case, we do this. 3. We do this. Okay, but the key thing to look at is 1 is this. 2 is a totally new case that we haven't ran into before. This. 3 is back to this. Oh, we haven't ran into this before either. Well, we use DP1. Alright, 3. For 3 we use DP1. And then this is new. Here. 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 That's DP3. For DP4 we use DP2. For DP2 was... yeah, but the rest is BS. The rest is... like the reverse of DP3. This is no good, because I want this to be over here, and this to be here, so I can... what? I wish I just had a visualized version of this. Move all the disks to the right stack using the middle stack. So, instead of trying to find a pattern, what we can do is designate where we want to move our current tower. How we know where we want to place it depends on the parity of the problem, I believe. Right? Okay. Case 1. N equals 1. We have one block. Whereas I'm gonna draw like some lines. Let's. Okay, I'm just gonna redo these blocks. I made them way too big in the first place. Boom. We choose 3 because it's odd. So if odd three equals 2. It's even. So we go boom, boom. No, 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 no. We go here, here, here. So this is wrong. Unless if it's special case. If 1, 3, if odd if even 3. We'll go here, here. And then n equals 3, we get so how do we go here, 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 here. We're in the wrong spot. So no, this is 3. Because for 4, here, 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 here. Two, we did this. One, we did this. 3, we did here, here. 3, we did this. 2, we did this. 4, we did 4, we did this. So it is if odd 3, no special cases. So our DP isn't the moves. Right? Because the moves change depending on parity. Bro, what is this question? Why can't I think of anything? The only thing I can think of is how sleepy I am. Oh, okay, so I have 3 stacks. But like I don't even know if we should define these stacks. It's like, what would we do? I feel like it would be hard to even brute force this. Like we have to use some sort of recursion here. Like, okay, all I see is this problem is like 2 steps. It's like before middle block, after middle block. And then this is moving the middle block to the end. What do we care about? 3 stacks. Our start and our stop. And our temp. So we have like a temporary Def Hanoi. Taking n. N equals 1. Start, end, temporary. Okay, wait, end. N equals 2. N, okay, wait. H of 1. So, okay, so we'll always have a starting location. Start, stop, temp. When H equals 1, our start is 1, our stop is 3, our temp is 2. When H is 2, we do H of 1. Start at 1, stop at 2, and we use 3 as temp, right? H of 1, Start at 1, stop at 2. We don't use temp at all. Then here we store one to two. And then we do H of 1. Wait, no. Then we move biggest to so fucking confused. From 1 to 2. Biggest to 3. So we just do 1, 3. Then we do H of start stop temp. Start at 1, we stop at 2. We can use 3 as temp. This is the block we're moving. To move. So it's H to move. Start. Stop. Temp. To move is basically just in. For n equals 1, we do 1. We want to move 1 from 1 to 3. We can use 2 as temp. And we basically just do if n minus 1 equals 0,
we do nothing. Return. We end the recursion, basically. Or we go to the next part of the recursion.
and then h n minus 1. So we do h0 we start at 1, we're gonna stop. Well, h0 doesn't do anything actually, so h0 just returns. Okay, and then we do restore 1 to 3. Yeah, we store this. That's it. H of 2, we do n minus 1. 3, we start at 1. We want to stop at 2. Use 3. And then we store this. And then we store this. And then we start at 1. Or we're doing 1. Wait. Yeah. 1 to 3. And then we start at 1. We're at 2. But we start at 2. We go to 3. We can use 1 as storage. And we store this. So every time we call Hanoi, we basically always call Hanoi as a Hanoi in start at 1, stop at 3, use 2. And then every time we call Hanoi, we should do moves dot append start stop. We can use a tuple because we will never modify this. Okay. So h of 3. Start, stop, temp. We start off by calling h of n minus 1, h of 2. Start. We want h of 2 to be at 2. Stop. That means we can use 3 as temp. H of 2 calls h of 1. Where we start. We stop at 3. We're going to use 2 as temp. h of 1 stores this. Then we store then we call h of 1 from 3 to 2. H of 2 call h of 1 from 1 to 2, store 1 to 3. Two to three. One is at 3 right now. We move 1 back to 2. We use 1 as temp. This stores 3 to 2. And then this ends this recursion. And then this means we can continue with this one. This one should store 1 to 3. And then we call h of 2. We are at 2. Want to move it to 3, use 1 as storage, which calls h of 1. We are at 2. Move to 1. Use 3 as storage. This returns 2 to 1. And then we can store 2 to 3. And then we call h of 1. We are at 1. We want to go to 3. We use 2 as storage. So we store 1 to 3. I think this works. Or at least we're recursing correctly. Now, the 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 crux of this now is how do we arrange these three numbers? Because we like flop around which numbers to which pillar to use as storage, where to start from, and where to stop from. Now, start is actually very simple. First, we need to add a check if n minus 1, if n minus 1 is equal to 0, return. No, it's just if n equals 0, return. Oh, I'm so gassy. And then we call Hanoi n minus 1. And we start Where do we start? Let's always start at 1. We always start at 1. We always stop at 3, and we always use 2 as storage. So then it looks like we flop storage and stop for this one. Let's look at this case first. This case we flop storage and stop, flop storage and stop. So this is interesting. Like every other one is the same. So we just flip flop. This is the parity shit that I was talking about. This is where the parity comes from, I think. Like even here, flop. So it should just be we start at the same place. Our stop becomes the temp, and we use stop as temp. And then we would store, so move, stop, append, start, stop. Because this should -1, so if it's 1, 3, 2, it would be 1, 2, 3. Wait, if n is 1, then it'd be 1, 3, 2, 1, and -1 is 0, so just return, and then we append 1 and 3. Yeah. And then this case is we flop start and temp. So in this case, it's here, start and temp, here, start and temp, here, start and temp. So we flop I already, it's like this. Hanoi, we flop start, so start becomes temp, and temp becomes start, stop stays the same. And then that's it. Because we test with for start, stop, temp, we go to 3, flop, stop and temp, go to 2, flop, start and temp, go to 1, flop, start and temp. Yeah, look at the parity here. And then this returns to 1 to 2. We'd also do 1 to 3. Then we do H1, flop temp and start. And then this would return 2 to 3. And then we would return 1 to 2. And then we'd go 2, 1 to 2, or we'd flop temp, stop, start. Wait. Yes. This will call H1 start like this, which will return 3 to 1. Then we return 3 to 2. And H1 temp stop start. So we return 1 to 2. And then we return 2 to 3. Oh no, 3 to 2. Recall. And no, I'm messing this up. So we already did this. So next we would do this one. H of 3, 2, 3, 1. And then we go do all this with BS again. I think this is right. Okay, wait, we can check for n equals 2. It's 1, 2, 1, 3, 2, 3. Okay, you need to have case 3 is 1, 3, 1, 2, 3, 2, 1, 3, 2, 1, 2, 3, 1, 3. It's 1, 2, 3, 4, 5, 6, 7. Okay. This one is just test it for check. 1, 2, 1, 3, 2, 3, 1, 2, 3, 1, 3, 2, 1, 2. Okay, the first half matched. Now all the flipping matches, right? Like 1 to 2, then 1 to 3, and then 2 to 3, and then 1 to 2, and then okay, this is supposed to have this entry here of 1 to 3. I think this is right though. This seems like it all matches up. Okay. Let's submit it, I guess. Okay. It worked. Oh my god, my head hurts. This question is a real mindfuck. Cause it's like, there's like, it's double recursion. Like, you recurse into two sides at once, and it's like one recurses first, and then you do the action, and then you recurse again. So it's like, oh my god. Like, you call the functions first. You call them until you get to n equals 0, and then you start running the functions backwards. So you start from 0, 1, 2. You run 0, run 1, run 2, run 3, run 4, etc., etc. Then after you ran through all of those, you call another set of functions all the way to 0, and then you start running those backwards as well. Oh, you call the functions first, run them, call, run. Okay, let's read. The following solution uses a recursive function that moves in disks from stack A to B to C using C. Yeah. From A to B. So start, stop, temp. The function assumes that all disks in stack B and C are larger than n disks in stack A, which will be moved. Assumes that all disks in stacks B and C larger than the n disks in stack A, which will be moved. If n equals 1, the function just moves a disk from stack A to B. Otherwise, the function recursively moves n minus 1 disks from stack A to C, then 1 disk from stack A to stack B, and finally n minus 1 disks from stack C to B. Using the function, we can solve the problem by moving n disks from left stack to right stack using the middle stack. The total number of moves will be 2n minus 1, which is optimal solution. Why is the solution optimal? Since we have to move the largest disk from the left stack to the right stack, we have to move all other disks to the middle stack first, so that, we figured this out. We have to move all of them to the middle so that we can move the last disk to the third stack, and then we iterate again. So that's basically this. What we're doing here every time is we're moving the biggest to somewhere, or at least like in the first call, what this function does is say move the biggest disk to the last pillar. So yeah, just basically move 1 to 3. um yeah, okay. After that, we have to move all other disks from the middle stack to the right stack. So yeah, so this function is basically manipulating everything to the center stack. This function, or this, then we call this, and this moves the first disk to the last stack, and then this is saying move all the disks from the second stack to the last stack. Oh. Alright, we got it. That took us an hour and a half. This was a hard problem. This was tough. This was like I felt like I had to like do so much visualization for this. And recursion is always tough, man. Recursion is always tough for me, at least. Like it's just hard to visualize what you need to do when you haven't finished running the program and then you have to start it again. You know, it's hard to predict what the outcome should be, especially if you have to nest it like this, where like there's multiple routes. Okay, well we got it. It's 12:17. There's let's check if Codeforces ever went back online. It's still not online. Can't do anything about that. But yeah, if y'all enjoyed this video at least, be sure to like and subscribe, and I'll see y'all guys tomorrow. Bye.